We are going to start module 1 of chapter 6. In this module, we shall discuss a new type of transformation which is known as canonical transformation. Sometimes it is found that some problems are described in terms of a new set of coordinates which express the problems in a difficult manner, but these problems can be expressed in a simpler form with the help of other set of coordinates. In such cases, it is required to transform the problems into simpler form. So, canonical transformations are needed. In Hamiltonian mechanics, it is found that it is unable to reduce the difficulty arising in solving the problems when it is treated in normal form. But with the help of canonical transformation, we can get advantage of using Hamiltonian. In this module, we shall discuss canonical transformation and related matters. First of all, necessity of such transformation will be discussed. Point transformation will be defined. We shall define canonical variable. Canonical transformation will be discussed and some properties of it will also be discussed. It is well known that cyclic coordinates have some advantages since they can be determined by integration only. So, it is desirable to have as many cyclic coordinates as possible in order to get advantage in the solution of a dynamical system within the framework of Hamiltonian mechanics. Generally, a given system of generalized coordinates reflect all the cyclic coordinates in Lagrangian or in Hamiltonian expressed in terms of those generalized coordinates, generalized velocities or generalized momenta. Sometimes it is very useful to switch over from the original set of coordinates in which the problem is expressed to another different set of coordinates in which the problem can be expressed in a simpler form. For example, in Lagrangian mechanics, if we are allowed to change the coordinates from small qi to qi dash, where small qi dash is a function of small q and time t, I varying from 1 to up to n, and if we redefine the Lagrangian of the system as Lagrangian L is a function of qi dot t transforms to L dash function of qi dash dot t, then the form of Euler-Lagrange equation remain the same in terms of both L and L dash. Please note that qi are the generalized coordinate, qi dot are the generalized velocity. Thus, a transformation in coordinates and momenta is needed which can transform normal looking Hamiltonian to a simple desired form of our choice. In such cases, solving the Hamilton's equations of motion becomes very easy. Now, we shall define configuration space and phase space. the instantaneous configuration of a dynamical system is described by the generalized coordinates. The n generalized coordinates small q1, small q2 up to small qn correspond to a particular point in the n dimensional space. The n dimensional space spanned by these n generalized coordinates of a dynamical system is called the configuration space of that system. The state of the system changes with time and the system point traces out a curve in moving through the configuration space. The curve traces out by the system point is known as trajectory or the path of the motion of the dynamical system. On the other hand, the phase space is spanned by the generalized coordinates as well as the generalized momenta. A 2n dimensional space spanned by n generalized coordinates as well as the corresponding n generalized momenta are called the phase space of that dynamical system. Now, we shall define point transformation. A transformation from a given set of generalized coordinates small q1, small q2 up to small qn to another set of generalized coordinates capital Q1, capital Q2 up to capital Qn is called a point transformation and is expressed as capital Qi equal to capital Qi function of small q1, small q2 up to small qn, I varying from 1, 2 up to n. It is called point transformation since it defines a point. In order that the inverse transformation small qi equal to small qi function of capital Q1, capital Q2 up to capital Qn for I equal to 1, 2 up to n also exists, the Jacobian of this transformation should not vanish. If the Jacobian vanishes, then the inverse transformation does not exist. This type of transformation is called point transformation as the set small q1, small q2 up to small qn represents a definite point in the configuration space spanned by these n number of small q coordinates and will lead to another definite point expressed by the transformation given by 6.1 in the configuration space spanned by the small n number of capital Q coordinates. Such a transformation preserves the form of Lagrange's equation of motion. Point transformations 6.1 and 6.2 are defined over the configuration space, but Hamilton's equations of motion describe the evolution of the state of a system in its phase space. Therefore, for Hamilton's equations of motion, we have to use some suitable phase space transformation, namely small q, small p, t transforms to capital Q, capital P, t defined by capital Qi equal to capital Qi function of small q1, q2 up to qn, small p1, small p2 up to small pn and t, and capital Pi equal to capital Pi is a function of small q1, small q2 up to small qn and small p1, small p2 up to small pn and t for I equal to 1, 2 up to n. In order to have a transformation which are physically meaningful phase space transformation, it would be quite logical to demand that new capital Q, capital P coordinates are canonical coordinates. That is, the transformation given by 6.3 should keep the form of Hamilton's equations of motion invariant. We may demand the invariance of Hamilton's principle under the transformation 6.3, that is delta integration T0 to T1 summation over I equal to 1 to n small pi into qi dot minus capital H function of small q p and t dt equal to delta integration T0 to T1 summation over I equal to 1 to n capital Pi capital Qi dot minus capital K function of capital Q capital P t dt, where capital K function of capital Q capital P t is the transformed Hamiltonian, whereas capital H function of small q small p t is the original Hamiltonian. Capital K is the transformed Hamiltonian under the transformation 6.3. The condition 6.4 immediately gives Hamilton's canonical equations of motion as capital Pi dot equal to minus first order partial derivative of capital K with respect to capital Qi, capital Qi dot equal to first order partial derivative of capital K with respect to capital Pi, I varying from 1, 2 up to n, which must be satisfied by the new coordinates and momenta which are capital Qi and capital Pi, showing that capital Q and capital P are the canonical coordinates. Now we define canonical variables. Two variables x function of t and y function of t are said to be canonical obviously in the Hamiltonian sense if x dot equal to first order partial derivative of capital K with respect to y and y dot equal to minus first order partial derivative of capital K with respect to x, where capital K is a function of small x, small y and t, and it defined over the space spanned by small x and y at any time t. Now we define canonical transformation. The phase space transformations given by 6.3 preserve the forms of the Hamilton's canonical equations of motion. That is, the Hamilton's canonical equations of motion remain invariant under the transformation given by 6.3 and are called canonical transformations. The phase space transformations 6.3 are called canonical if capital Qi dot equal to first order partial derivative of capital K with respect to capital Pi and capital Pi dot equal to minus of first order partial derivative of capital K with respect to capital Qi, I varying from 1, 2 up to n, where capital K function of x, y and t is a function defined over the space spanned by capital Q and capital P at a time t. The function capital K plays the role of Hamiltonian. Thus, to look for a set of generalized coordinates in terms of which the system simplifies as much as possible, the idea of canonical transformations developed. If the canonical transformation does not include the time t explicitly, the transformation is known as restricted canonical transformation. Now, one can remark that identity transformation is canonical. If a transformation is canonical, its inverse is also so. Two successive canonical transformations constitute a canonical transformation. Now, we shall discuss properties of canonical transformation. The Jacobian determinant of the univalent canonical transformation is unity. All univalent transformations form a group with respect to the composition defined by C1 star C2 equal to C1 C2, where C1 C2 are any two canonical transformations and C1 C2 denotes the transformations that are performed in sequence. Canonical transformations preserve the form of Hamilton's equations of motion, which is very much helpful. Moreover, it can be used to reduce the number of degrees of freedom of a dynamical system by exposing the invariant quantities or quantities which are almost invariant. Now, we shall discuss Poincare theorem. Under canonical transformation, the integral capital J equal to double integration over S summation over I dqi dpi remains invariant, where capital S is a two-dimensional surface in phase space. Poincare theorem plays an important role in classical mechanics, particularly in canonical transformations. It is well known that under canonical transformations, the form of Hamilton's equations of motion remain invariant. In searching if there are some other invariants under the canonical transformations, Poincare found the integral invariance, which is popularly known as Poincare theorem. In a two-dimensional surface, any point can be uniquely specified with the help of two parameters. Let u and v the two such parameters. So, we can specify qi and pi in terms of u and v as generalized coordinate qi is a function of u and v, whereas generalized momentum pi is a function of u and v. U and v are the parameters. qi and pi are the old canonical variables. Now, double integration over S summation over I dqi into dpi can be written as double integration over S summation over I Jacobian qi comma pi with respect to u comma v into du dv. Here we are considering the surface integral. The Jacobian can be written in explicit form and we get equation 6.27. Now, consider the canonical transformation given by capital Q suffix k, which is a function of generalized coordinate q, generalized momentum p and time t. Similarly, capital P suffix k is a function of small q, small p and time t. In this case, let us calculate summation over k d capital Q k into d capital P k. With the help of differential calculus, we can get equation 6.28. This is the Jacobian of capital Q k comma capital P k with respect to u and v. So, if capital J remains invariant under canonical transformations, we must have double integration over S summation over I dqi into dpi equal to double integration over S summation over k d capital Q suffix k into d capital P suffix k. We have to prove this relation. That is, we have to prove that these two surface integrals become equal. If we substitute the expression already obtained for dqi into dpi and d capital Qk into d capital Pk, then we get the next equation. Since the surface S is arbitrary, so we have to prove this identity given by equation 6.29. Thus, to prove Poincare theorem, that is J remains invariant under canonical transformation, if we can prove the identity given by 6.29, then we can prove the invariance of integrals given in the equation double integration over S summation over I dqi into dpi equal to double integration over S summation over k d capital Qk into d capital Pk. Using some manipulation of determinant and the generating function of second kind, we can prove this identity easily. It will take some time. You can get more details about the proof from your content, and also you can get help from the reference books and also e-books available in the website. Canonical transformations play an important role in classical mechanics, particularly in Hamiltonian mechanics. In this module, we have discussed the detail about it. For this purpose, we have defined the canonical variable, point transformation, canonical transformation, its properties, and also the Poincare theorem has been discussed in detail.